This video is about using properties of logarithms to expand or condense logarithmic expressions. Most important to this is the product and division properties and the power property. Let's get started. Here is a quick overview of some of the properties about logarithms we've talked about so far, and then we'll build and emphasize the new stuff. When you think about log base b of a is equal to x, what you're thinking of is b to what power is equal to a. So b, the base of the logarithm, is the base of the exponent. Okay? And you're asking yourself to what power, which means that x is the exponent, and you're wondering b to what power is a, and so a is the number that's inside the parentheses. Okay, that's writing it from a logarithmic equation to an exponential equation. Okay, these first three we've hit in a previous video. Okay, so simply put, b to what power is b? It's equal to 1. That's the identity property. Okay, b to what power is 1? Well, anything, so any base to the 0th power is 1. So log base b of 1 is 0. Next, if a is equal to b, then you can raise both to the same power. A to the n equals b to the n. Okay? And what that means as a logarithm rule, that log base b of b to the n is equal to n. Okay? Because you're asking yourself, b to what power is b to the n? And that's the nth power. Okay? Or written differently, this one looks kind of funny, but b to the power of log base b of n is b to what power is, anyway, so you also get n this way as well, because log base b of n is asking b to what power is n, and you're raising b to that power, and so you get n. That was like really dense to kind of understand that, but that's it. Okay, the most important thing that I want to talk about in this video are the next bit. So these three are all kind of together in how I think about it, and then the power rule is separate but equally important. Okay, those are both really important. And the way that I understand, let's start with the product rule. Okay, all of these rules come from exponent rules. Okay, and it comes from the fact that b to the m times b to the n is equal to b to the m plus n. You add the exponents when you're multiplying two exponential expressions. Okay, and what that looks like as logarithms is that the log base b of m plus the log base b of n is equal to the log base b of m times n. Okay, so because the log base b of m is an exponent and the log base b of n is an exponent, adding the exponents is the same as, multiplication, between two, numbers. Okay, so addition between the logarithms is the same as multiplication inside the parentheses. Okay, and we get that same thing. The log, if you have log of m times n, is just equal to the log base b of m plus the log base b of n. Okay, here's an example of that. Log base 3 of 9x, we notice, oh, hey, I have multiplication between 9 and x, and so I can expand this and write log base 3 of 9 plus the log base 3 of x. Okay, now we could keep going because the log base 3 of 9, 9 is a power of 3. It's 3 squared. And so log base 3 of 9 is 2 because 3 squared is 9. And so you could write it like this. Okay, but the piece that we're focused on in this property is this, hey, I can expand this because I have multiplication. Now, to me and my thinking, that's very, very similar to the quotient rule. Okay, notice that we have b to the mth power divided by b to the nth power, that I can write that as b to the m minus n, it's top minus bottom. Okay, that's the quotient rule for exponents. And what that looks like with logarithms is the log base b of m over n is equal to log base b of m minus the log base b of n. So again, it's this top minus bottom. The logarithm is an exponent, so I can think about subtracting exponents is the same as division of normal numbers. Okay, or the log base b of m minus the log base b of n is the log base b of m divided by n. An example of that is, I'm not sure why the base of 1/4 was chosen, but it doesn't matter what the base is. Log base 1/4 of 4/5 is equal to log base 1/4 of 4, the numerator, minus the log base 1/4 of 5, the denominator. Notice they were subtracting. They were subtracting because we have top minus bottom. Now, the way I think about these, I pull them both together into the same thinking. And I think to myself, if it's positive, it goes in the numerator. If it's negative, it goes in the denominator. Okay, and that thinking really helps me out as I'm doing logarithms. Okay, it makes really hard problems a lot simpler to think about. Okay, positive numerator, negative denominator. If there's more than one positive, I'm just multiplying together as if they're both in the numerator. Okay, and my thinking about looking at it in that direction helps me to kind of simplify these negative exponents ideas. And saying that, hey, this n is in the denominator, and that's why it's a negative log base b of n. Okay, that's what I call the product and quotient rule. This positive numerator, negative denominator. That's one huge piece of this expanding and condensing of logarithmic equations. Okay, I'm going to switch gears here and pick a new color to change gears. Okay, and talk about the power rule. That's a separate but equally important concept. Okay, the power rule is a little bit different for exponents and for logarithms, meaning for exponents, b to the m to the n is where you multiply them together. That's true. Okay, but the power rule for logarithms behaves a little bit differently. Okay, because the logarithmic expression is an exponent. Okay, I'm asking b to what power is b to the m. I can take the exponent here and bring it in the front of the logarithm. Okay, so I can write this as n times log base b of m. Okay, that the exponent can go in the front as a coefficient of a logarithmic expression. Okay, like over here, this exponent of x can go to the front and become a coefficient of the logarithmic expression. Okay, and that can go either direction, by the way. Okay, so if I'm given it in this format with the coefficient, I could put it up as an exponent and go backwards. I can go either direction with that property. Okay, and I guess both of these I can go either direction. Okay, and that's kind of the two pieces that I'll be looking at doing a product quotient rule or power rule, and kind of doing one and then the other, whether I'm expanding or condensing. So with that kind of front-loaded, let's look at applying these two big ideas to expand and condense logarithmic expressions and equations. Okay, let's start easy. Let's reduce each expression to a single logarithm. That means I'm going to condense these logarithmic expressions. Okay, and again, my rule of thumb is positive numerator, negative denominator. And I'll write it as a single logarithm. So this is log, and I'll keep the same base. There's no base written here, so it's base 10, but I don't have to write that. Now these are both positives. They both kind of stay in the numerator in my mind, and I just multiply 5 times 7. It's multiplication and division. I will not be adding these inside the parentheses. So 5 times 7 is 35. Okay, letter B, the log of 3 minus the log of 9, I'll write as a single logarithm. This is log base 10, and I have, if it's positive, it goes in the numerator, negative in the denominator. Now I'm going to simplify this just because I really want to. At 3/9 is the same as 1/3. I don't know if you have to do that in this problem, but I'm going to, because if you can simplify, you should simplify. Okay, log of 15 minus the log of 5. They have the same base. I'll write it as a log. And I have the positive log, positive log of 15 means that 15 goes in the numerator. The negative log 5 means the 5 goes in the denominator. Okay, and 15 over 5 is equal to 3, so I get the log of 3. Okay, and returning back to the log of 8 plus the log of 14. These are both positive, so I will multiply them inside the parenthesis. I have the log of the same base 10, of 8 times 14. 8 times 14 is 112, so I get the log of 112. Okay, and that's at a simple, just two terms. Again, addition is multiplication, subtraction is division, but if they get longer, positive numerator, negative denominator. Okay, here's where they get a little bit longer. I have the log of 3 plus the log of 4 plus the log of 5 minus the log of 6 equals 1. I'm showing that. So I'm just going to write over here on this left-hand side, right-hand side. So I'm going to condense these into a single logarithm. Okay, so they all have the same base, a single logarithm. And I have a subtraction, so I have to think about division bar. And if it's positive, it goes in the numerator. So the 3 is a positive, and so it goes like this. This logarithm is positive. So 3 goes in the numerator times the 4. The log of 4 is positive. The 4 goes in the numerator. The log of 5 is positive, so the 5 goes in the numerator. And the log of 6 is negative, so the 6 goes in the denominator. Okay, 3 times 4 is 12. 12 times 5 is 60. So what I get is the log of 60 divided by 6 is, now 60 divided by 6 is 10, and I get the log of 10. All right? Now, there's no logarithm, like the base is not written, and so it's base 10. And from the identity property, log base 10 of 10 is equal to 1, because 10 to the first power equals 10. And so this is equal to 1, and that's why it equals 1. Okay, but that positive numerator, negative denominator is really useful for us. Okay, number 2, use log properties to rewrite an expanded form. I'm going to expand this to be larger. Okay, the log a root b over c to the 6th power. Okay, so I think this is the first time we're dealing with powers as well. Okay, the first thing that I see is that I have the log of some stuff, and I want to expand this. And so I think to myself, the numerator is positive, and the denominators will be negative. So I will write the log, and it's the log of each term. The log of a, that's in the numerator, plus, because b is in the numerator, the log of the square root of b. But c squared is in the denominator, so I'm going to subtract the log of c to the 6th. Okay, and the reason I can do that, that's what I call the product and division properties. Okay, so once I dealt with that, I'm now going to think about the power properties. Okay, but I don't quite have a power for b because it's a square root. But I know the square root is the same as the 1/2 power. So rewriting this, so I can write log of b to the 1/2 power minus log of c to the 6th. That's kind of rewriting the square root is the same as a 1/2 power. Okay, and now that I have clear powers, I can bring these powers in the front as coefficients. And I get the log of a plus 1/2 the log of b minus 6 times the log of c. Okay, and that's using the power property. By the way, it'd be a good practice for us to take that expanded form and put it back into a condensed form to see if you get the same thing back and forth. You should be able to go backwards and forwards with this once you get better at it. Express as a single logarithm. That means to condense. Okay, I have the log of x plus 4 log y minus 5 log z. And the first thing that I see is that I have some coefficients. Okay, I look for those first before I put it into one into one logarithm, I first look for coefficients, and I have them here. And so I'll take those coefficients and use the power property to make them exponents. So it's easier for me to condense it later. So I get the log of x plus the log of y to the fourth minus the log of z to the fifth. Okay, and that's by the power property. Okay, and now that I have the log of something plus the log of something minus the log of something, I'm now going to use that product and division property at the same time and write this as a single logarithm. Okay, the log of x is positive, so x goes in the numerator. The log of y to the fourth is positive, so y to the fourth goes in the numerator. And the log of z to the fifth is negative, so z to the fifth goes in the denominator, and I'm done. Okay, so really those two really big properties, the power property and this product and division property, is what you use to condense or expand these logarithmic expressions. In number 4, we'll express as a single logarithm. Means we're going to condense it together, and I have my eye on this as my answer. Okay, and I notice I have a big square root. So I'm going to kind of leave this 1/2 by itself for a little bit, and focus on what's in the square brackets. Again, I look like I did before for coefficients. I have a coefficient of 4 here and a coefficient of 4 here, and so I'll make those exponents so it's easier for me later. So the 1/2 will just hang out for a while. And writing the 4 as an exponent, I have the natural log of a to the fourth, plus the natural log of b. Okay, this is in parentheses, although I don't need those parentheses, minus the natural log of c to the fourth. Okay, I just took those coefficients and made them exponents because I want that as I condense. Okay, and then I don't really need the parentheses. Like, it doesn't change the problem at all. I think it's easier to think about it that way. And then I'll combine all of this into one logarithm with the same base as before, which is the natural log. Okay, the natural log of a to the fourth is positive, so a to the fourth goes in the numerator. The natural log of b is positive, so b goes in the numerator. And the natural log of c to the fourth is negative, so c to the fourth goes in the denominator. So I'm kind of halfway done. Okay, and I'm going to look at, now I'm going to take care of, now that I have this piece right here, the same as this piece here, I'm now going to shift my focus and deal with this 1/2 power. Okay, I'm now going to think about this 1/2 as a coefficient, which I'll put up and make an exponent of this big expression here. So I have the natural log of a to the fourth b over c to the fourth to the 1/2 power, but I know that the 1/2 power is the same as the square root. So I get the natural log of the square root of a to the fourth b over c to the fourth. All right. So really it's that power property and the product and division properties working, back and forth to do a lot of these problems. Let's finish this video off with an applied problem. Every year, Mr. Lewis, that's me, buys 130 red pens for grading at the beginning of each of the year. That's actually not true, but I do usually buy more pens for grading. He figures that the number of pens decreases exponentially at about 9% each week. When he has only 10 left, he goes and buys more. So what's an exponential equation that would model this situation? Well, I'll name the function f of x. Okay, the initial number that I start with is 130. Okay, now the tricky part has to do with the base of the exponent. Okay, it decreases exponentially at about 9% each week. Okay, and I think about that as a percent decrease. So from 1, which would be a 1 would means I don't change, at all. Okay, my number of pens don't change at all. I'm decreasing, so subtract 9%. So 9% as a decimal is 0.09. Okay, and that's my function. I get equal to 130 times 0.91 to the x. So every week, I have 91% of the pens I had the previous week, and that just goes on and on and on until I have 10 pens left, and then I go buy more, I guess. Okay, so to begin solving this for when I have 10 left, I'm going to put 10 in here for f of x, the number of pens I have. Okay, and I'm going to begin solving this. The way I solve this is I want to get this x by itself, but I'll first divide both sides by 130, and I have 10 over 130 is equal to 0.91 to the power of x. Okay, and now this is written as a true exponential equation where I have something is equal to a base to a power, and I'll rewrite this as an exponent. And I'll rewrite this as a logarithm. Okay, log base, the base of the exponent is 0.91. Of what number? Well, it's 10 over 130 is equal to the exponent of x. So 0.91 to the x power, or to what power, is 10 over 130, and that's written as a logarithmic equation. Okay, now at this point, honestly, I would go to my calculator and plug it in and find the answer. Okay, we're going to kind of just take a side step really quickly, make a connection with what we're currently doing, and that is to use properties of logarithms to expand this, just because we can. Okay, to expand this, I have tens in the numerator, so I have the log base 0.91 of 10, and then 130 is in the denominator, so I have minus the log base 0.91 of 130. So subtracting, I have numerator minus denominator, or tens in the numerator because it's positive. 130 is minus because it's in the denominator. Okay, equals x. Okay, now when I plug this into my calculator, I'm going to plug in this one right here because it's easier for me. Okay, and in my calculator, math A, or math alpha math, that's kind of a quick way to do it on the TID4, and that you get 27.2 weeks. So according to this problem, after 27.2 weeks, I have 10 pens left, and I'm going to buy more pens. All right, this video is about expanding and condensing logarithmic expressions. Thank you so much for watching.